Trees in every country. Trees, you know we can work together and learn what we need to meet the challenge.
Hello, and welcome to the ISA Conference Rewind video podcast series. I'm Tanisha Price, instructional designer with the International Society of Arboriculture. Today, ISA is proud to bring you a presentation by Jason Lubar and Laura Hansplant entitled Growing and Anchoring Trees on Elevated Structures, Raising Tree Canopies to New Heights. This talk was originally given at the 2021 ISA Virtual Conference, so the views seen here are those of the presenters. Now, sit back and enjoy.
Hi, everybody. Thanks for joining us, and welcome to Growing and Anchoring Trees on Elevated Structures, Raising Tree Canopies to New Heights.
Thank you, everybody. It's a pleasure to be here today. My name is Laura Hansplant. I'm a landscape architect, and I've been specializing in sustainable design for, close to 20 years now. It's been a long time, Jason. Specializing in elevated landscapes, green roofs and their kin, including trees, for about the last decade. So real happy to be here.
And I'm Jason Lubar. I'm the Associate Director for Urban Forestry at Morris Arboretum of the University of Pennsylvania. I'm a BCMA. I'm the president of the Pendle chapter of ISA, and I'm track qualified, TPAC qualified, ASCA member, and I just love trees. And part of what I do, most of what I do is consulting, and it's great consulting on these projects where we're looking at green roofs, growing trees on elevated structures, that kind of thing. And that's what we're sharing with you today.
So our objectives today, we'd like to talk a little bit about why do we care? What are some of the challenges, but the benefits and opportunities of growing trees on structure? What are the kind of risks we need to think about, and how do we mitigate that? What are some of the technical issues? We'll take a little bit of a deeper dive into soil issues, engineering and weight issues, and maintenance issues that come along with growing trees at these kinds of heights and on structure. And we'll think creatively, practically, and also maybe a little bit creatively about how to anchor trees on structure.
Yeah, so what we're going to do today is go through these objectives. Why are we planting trees on roofs anyway? What species are good perhaps for planting on rooftops? What about the tree roots themselves? What kind of rooting volume and soil volume do they need? How do we anticipate tree growth and weight over time? What about wind and tree anchoring? Because, we are growing these trees 20 stories up, 30 stories up, perhaps 100 stories up. Installation and management issues, and pretty much the future of where we see this going and how you can be involved with a project team to put trees on rooftops. Now, why trees on roofs? Well, as you probably know, in urban areas, there's an urban heat island effect. So putting trees on rooftops can benefit the climate by cooling it down, providing all the benefits that you're probably aware of for health and for comfort. Also, in cities and urban areas, of course, there's so much impervious surface that it's hard to find a place for trees. So we're looking at sticking trees everywhere we can, including on top of rooftops, because really, as you fly over a city, rooftops are a wasted space. There's not much on top of them. And it's really valuable space because it's in the middle of our cities, and our cities have about 20% in total, the total area, about 20% impervious surface. So putting trees on rooftops can really provide us and our cities with a lot of the benefits that we seek from trees.
Well, and thinking beyond that, actually, where I find talking with developers and property owners, where they get very excited about the potential for the complementary spaces that we can create on elevation that complement and provide slightly different benefits to what you get on the ground. So, as a landscape architect, I sometimes find it very difficult, especially in older urban areas, to find places where we physically can plant trees on the ground in dense urban downtown city centers. But these elevated spaces, can be technically challenging, but they create great prospects, great opportunity for outdoor amenity, and trees are an important part of that. And people get excited about those possibilities.
And it's also inspiring to be on the ground and look up and just see greenery and trees up there, where before it was just infrastructure, gray infrastructure.
And, conversely, Jason, there's something very lovely about being in a space like where you see in this picture on the right and having the prospect over the city, over the skyline, but yet being a little bit sheltered from the kind of public quality of the street. There's this nice, exclusive, comfortable feel that people find, that I hear people talk about. So what are some of the challenges? Well, as a landscape architect, I often get asked, well, what bloom color do you want? Like what size and aesthetic do you want from a tree selection? And when we're talking about trees on structure, we actually start in a completely different direction. And we say, gosh, how much soil volume can we provide? And what does that mean for tree size? What kind of weight can the structural engineer handle in his structural design and in the architectural design? And what does that mean for tree size and soil depth? How exposed is it? Wind is a big deal. And its implication for which species we might protect, one that's maybe stronger wooded or that adapts more gracefully to kind of a mountaintop situation. What are the unique properties of engineered soil? They tend to be higher pH, lower nutrients, and really well draining. What does that mean for our tree selection? We need to water them. People always say, can I get away with just rainfall? But typically for woody plants and especially trees, the answer is no. You will need supplemental water. And then what's our timing and how do we coordinate the maintenance? And we'll talk about more about all these issues as we go forward.
Right, but let's begin with the root of the issue, roots. We need to understand, when I say we, arborists, and since you're usually on a design team, you need to be able to educate engineers in your team about roots and how to design and grow trees to maturity in these restricted conditions. So as people think of tree roots as the tree on the left, growing down like it's almost an upside down version of the canopy. But as we know, tree roots like growing as we see on the right there, which is really important for you, well, not for you, but your team to understand.
And it's a good thing for on structure. That's a good thing. The shallow and wide.
And, you have to be able to explain to engineers who might not understand how tree roots grow, or your architects or even landscape architects, that, usually in nature, tree roots don't grow that deep. And they usually spread very wide, a lot wider than most people think. And whatever you're designing for has to accommodate that. And also that there's this idea of a tap root that everybody has ingrained in their head that and people are worried about when you're growing a tree on a rooftop. Won't the tap root break in through the rooftop? So you have to be aware of how roots really grow and be able to educate your team on, the reality of root growth. So let's look at the different types of roots we have. We have the structural root zone and the biological root zone, and how to accommodate these zones in your design. Anchorage really depends primarily on 7 items, and I'll just go through them quickly here. The soil that you're using must resist the fracturing. In other words, the shear strength of the soil needs to be adequate to hold the tree upright. The windward roots of the tree, the ones that are growing against the wind, must resist pulling out of the ground and breaking in tension as they move with the wind. Likewise, the leeward roots must resist buckling in compression, and that soil underneath it has to give the roots something to hold on to and something to press against, so the tree won't move too much. The roots must be strong in cross sections, so you have to have good root growth, and large roots near the stem of the tree must resist delamination near the soil. So the root contact with the soil, and the soil is very important. And the soil must remain at less than the water content of its plasticity. In other words, once soils become too wet and the tree starts moving in the wind, they become plastic. So it's easier for the tree to fall over than with well-drained soil.
Fortunately, most engineered soils for elevated landscapes are well drained, but not very cohesive. So we'll get to that.
Right. So the structural root zone are these large woody roots, rapidly tapering woody roots that are closest to the trunk. And establishing these roots early and designing around them helps establish proper anchoring within this system that you're creating to hold the trees. And you have to talk also about the biological root zone, and all this biology within the soil must be healthy in order for the tree to survive. In a teaspoonful of healthy soil, there are more microbes in that healthy soil than there are people on the planet. And a handful of healthy soil, there's more biodiversity in just the bacterial community than you will find in all the animals in the Amazon forest. And people have to realize that when they're talking about soils and the biological root zone, because really good soils make good trees. That's true for the trees that we plant on the ground. It's also true that for trees that we're going to plant on top of buildings as well. So let's talk about soil. All the soil on an elevated rooftop project is going to be manufactured and engineered. And this creates some problems and some opportunities that we're going to go into later on in the presentation. But the main thing is providing, or a main thing is providing as much soil as possible for that tree. So as we see here, larger trees need more soil. And this is, of course, based on a lot of work that's been done on at-ground trees, but the same is true for trees on elevated surfaces.
And so, as designers, we really rely on research like the research here that's presented by James Urban on what, and summarizing, in this case, you're right, street tree studies on how much volume you need in order to maintain a given size. And the questions out there really for further research are, how much sharing can trees do? If we pair them up in a trench, can we get some efficiency and some synergies which better allow for us to optimize volumes or get better sizes, with more confidence in the volume we have, but ultimately, when we're talking with architects and designers who may be your clients, trees that have enough soil probably look something like this. And I tell clients that usually the size of the planter, assuming you've got 2.5 or 3 feet of soil, the correct volume probably needs to come out to where the ultimate drip line is. There's a correlation there. And that, again, that's kind of not a surprise, but you need to remind people. And the shape can change. The placement of the tree to some extent can shift within that planter volume, but we need to be providing the volume. So it looks like this. You go to the next slide. Now you're all going to laugh. You've all probably seen this. It does not look like this. You'd be amazed at how many designers right off draw little squares on the rooftops for trees, forgetting that you can't grow a tree in a coffee cup, and or they'll draw little squares in pavement, assuming that there's all sorts of soil underneath the pavement, which isn't necessarily true, not unless we've deliberately designed for it. So on structure, we need to deliberately design for all the soil. So here's one possible creative outcome. This is a green roofing construction. The blue stacked material you see is lightweight insulation. It's creating lightweight terrain within the weight limits we have. The soil's not been placed. So the tree goes in this scooped out area. And then there will be probably 12 or 18 inches of soil, 8 inches of soil, the designer can decide, that gets placed on top of that insulation. So the root volume has a deep zone near the tree and a shallow zone throughout the rest of the landscape for the feeder roots. That's one solution. Go to the next slide. Here's another one. This is at Lakeside Prospect Park in New York. And here you see a lightweight landscape that's going in for a new park facility, which sort of the building slides into the landscape. And the white circled areas, again, are areas for trees. You can see they've carved out deeper areas for the tree root ball and the structural root. And so the key question that comes up for us when we're thinking as arborists or as designers is, how big do those need to be? And I would argue these are really for a smaller tree, that in order to accommodate the appropriate structural roots and the supporting structural root flare, as Jason was saying, that those holes need to be sized wide enough that the tree can maintain its stability, in addition to whatever it's doing with its feeder roots and the shallow root zones in between. Make
And
sense?
just for you arborists, you see that most of the area is this lightweight styrofoam, and the soil is put, the growth medium, it's not really soil, is put on top of that. So you might think that it's, we're using a lot of soil media on these rooftops, but actually the blue foam is lighter, and it provides a substrate to hold that soil down and not weigh down the rooftop.
Yeah, it lets us create terrain without adding weight. So here it is. Here's what it looks like when it's finished. This is that same landscape finish. So the trees and the shrubs that you see on the right-hand side of the photo are all on structure. Those are newly planted on structure. Actually, the trees in the foreground on the left are also on structure. So, and as Jason said, the methodology typically tends to be more breadth, less depth. That's when I was joking that the tree root geometry sort of works in our favor.
All right, so how else can we achieve the goals of providing enough soil volume on elevated rooftops? And you can do this. I'm not hawking any particular product, but generally soil cells are really useful on rooftops because they're lightweight, they hold the soil in. Designers can design around them. In other words, putting, as you see on the right there, putting a patio or other infrastructure on top of the soil, and it's still being light enough that it achieves the engineering goals for the building. So soil cells might be a great thing to use on top of rooftop structures, as long as the engineers understand how to design with them.
If anybody here is in product development or knows someone who's in product development for these kinds of soil cells, modules, it'd be great to have more adaptions and more accessories that let them work better on structure. It's a little finicky taking these on-ground products and getting them on a rooftop. So more good conversations.
So let's talk about the forces on trees, because you're going to be part of a team, and there's going to be probably engineers on that team, and you don't have to understand this, but you have to understand it conceptually. There's static and dynamic forces. So let's talk about static forces. Those, their weight, the weight of the tree, the weight of the water, the weight of the rooftop, the roof material. And this is all reasonably understood in the industry, in the engineering industry. And they're pretty much quantitatively calculated, but for the engineers don't know how much weight a mature tree has. You could say they know how much weight the soil is, but it may be up to you to determine, well, this red maple, we expect it to achieve this size, and this is the weight of that tree. So the engineers understand what kind of static load that imparts to the rooftop.
So soil weight, green roof soil, engineered soil is typically significantly lighter than normal soil. So, a common range in the industry is between 65 and 90 pounds per cubic foot. 80 to 85 is pretty safe. As you get down closer to 60, you tend to add cost because the growing medium becomes more expensive to adjust the recipe as the weight gets lighter. Normal soil, obviously, significantly heavier. And so even though, interestingly, that soil, that growing media costs more, it pays off because weight equals cost in other aspects of the building design. As weights get heavier, the structural engineering and gets more robust, the size of the beams goes up. That affects architects' ceiling heights. So we find that optimizing the weight is absolutely key to being able to successfully keep trees in projects when we're talking about green roofs. So the lightweight soil pays off. So the soil weight, then when you translate the ideal depths, for your size of tree to weight, you get a formula that says something like 30 to 36 inches. That translates to about 240, 250 pounds per square foot for saturated lightweight growing media. So think about those numbers for a second. 240, 250, somewhere in there is the weight of your soil. People worry about the weight of the tree, but I'm going to tell you right now that the weight of the soil is the far bigger driver. If you think about the tree, when you look at the weight of a 20-inch tree, and 3 tons sounds like a lot of weight, but when you convert that over the structural root plate, the bearing root plate of the tree itself, and this is where the math calls for some professional judgment, but usually you end somewhere between 20 pounds, 30 pounds per square foot, maybe 40 pounds for a really big tree. So 20, 30, 40 pounds per square foot is a small component compared to the saturated weight of the soil we were just talking about. So usually we end up somewhere around 300 pounds per square foot ish. But then, that's where we start horse trading on tree height, tree size, soil depth, and our professional judgment, becomes a key part of that conversation.
Right. As we spoke about earlier, not every tree is adapted to these rooftop soil conditions. Ridgetop trees that grow on ridge tops, well-drained, granular soil, or that kind of soil mimics what we're putting on rooftops. But we really need more research on what types of soil are needed to grow these large trees on top of roofs. We do have specifications. We need to get better specifications. And people think, well, let's add clay and things like that. But you have to be careful because, as Laura said, it drives up the weight of the growing medium. So we do have specifications now, but we as an industry definitely need better soil specifications for growing trees on rooftops.
I'll add, Jason, those soils tend to be neutral to alkaline. So species selection tends to bias towards trees which are adapted for limestone ecologies.
Right, instead of acid ecologies.
Correct.
But that we'll talk about that later. But healthy soil to me has always been living soil. For me, that's the soil is the most important part of this equation. because trees evolve with this underground food web, and they really need these fungal associations, these living organisms associations to survive. Uh, on rooftops, that means supporting this biological component with this soil that's mixed and engineered. It doesn't mean just adding more organic matter to the soil, because that can be counterproductive, because that organic matter may be used up. May make the soil more friable, so it might destabilize the tree. What it does mean is that we as an industry need to develop specifications that add this living component to this dead soil as much as possible. It may mean that we need to go to a forest and dig up healthy soil, some healthy soil, and sort of seed it in, put it on top of this manufactured soil to start the process of introducing these living organisms into the soil. So really, we need a little more help with this, and a little better specification to assure long-term tree health. So we talked about the static forces, the weight of the tree, the weight of the soil, the weight of water. Dynamic forces are really some of the great unknowns when we're designing rooftop tree gardens, because engineers like to have everything quantifiable, and the dynamic forces do present a challenge, because on trees, especially large trees, they're less understood and there's less guidance in the engineering documents. However, as we all know, as the building height increases, usually in urban areas, the wind load increases, the wind speed increases. And especially when it goes around buildings that are nearby, you can have very complex wind conditions. But the wind loading on buildings is really well understood in, the engineers really understand it in building design. But so we have to consider those dynamic forces of wind when we design these pits. And up here in the right, you can see Klaus Mathek. He's an engineer. I'm sure a lot of you heard of him. And this is saying that these dynamic forces on trees are less understood, a lot less understood, even in the engineering communities. And he worked to quantify the dynamic forces on the tree root system. And as you could imagine, those forces, when the tree bends, concentrates on that structural root plate. And these sort of conditions can become very complex from a design standpoint and from an engineering standpoint. So again, when the wind comes in from one side, the opposite side pushes down on that roof structure. Now, with what kind of force? Well, it depends on the speed of the wind, the size of the tree, if it has leaves or not. It depends on a lot of things. Conversely, the opposite side of that root plate sort of lifts up in response to the wind. So really, we have to understand these dynamic forces and design for them as well. And it can become very complex. Here we can see the wind coming up over a building. And as you can see, the front of that building is on the rooftop is taking a lot more wind pressure than the back of the building. Okay, so we need to anticipate that in our designs. And yes, this may be beyond your ability to do this, the engineering calculations, but as part of the team, you have to bring up these issues about wind. This here is it's a computerized wind flow or wind pressure model. And so you can see how on the left, the wind's coming in, and you can see the pressure on the front part of the rooftop of that building. And so this is a computer simulation. However, this is pretty expensive to do with three-dimensional models. So most projects can't afford it. So ideally, if you're putting on large trees on rooftop structures, the wind should be modeled and should consider all the adjacent buildings. But a lot of times it's just not done.
So here, I'll give you some practical examples, which I think are illuminating. This is a picture taken at Sierra Green, an elevated park in Philadelphia that's about 12 stories above grade. And the wind in this picture comes from the right to the left. And you would think that the upwind tree would be the most effective, but actually, if you look, it's the left-hand tree, the downwind tree, which is smaller and more affected by the wind. That's actually a replacement tree because the original one snapped. These trees were, the original trees anyway, were all installed at the same time. They're honey locusts, which we thought would do well in the alkaline soils and kind of the wet, dry conditions. Fit the conditions of the site. But you can see here that the raised topography you see on the far right of the picture, where those yellow cones are, is actually creating a little bit of a shelter belt effect, if you will, for the downwind, the first tree in downwind. And that it's only as you move over towards the left that I believe that the wind speed is picking up. And so in this case, it's the downwind tree that's the most affected. Go to the next slide. Kind of counterintuitive. The other thing we've noticed, this is the same project on the other side of the park. Look at how the tree leans away from the building. So this is I believe this is the unexpected effect of downdrafts. The wind is coming from behind the photographer, blowing out towards the skyline. You see the prevailing winds come from behind the viewer out to the background there. But the honey locusts in this case are not bending. We're not seeing that response to the prevailing wind. We're seeing it from the downdraft of the building. And we had to, in this case, replace a tree or cable them a little longer to let them adapt to the existing wind conditions, longer than we would have on the ground.
Right. So the bottom line is it's wind conditions are very complex. And if you are involved with a team, it may be beneficial for you to really push for a wind study, because the buildings around where your project site really can make complex wind conditions.
And to be adaptable.
All right, so we talked about, Laura just said, well, we had to anchor the trees and cable the trees to the ground a little longer than usual. Well, let's talk about tree anchoring systems on top of rooftops, because this is a safety issue. You don't want a 10-inch red maple getting lifted up and falling 20 stories to the street below. So anchoring the trees is really important. So these above ground systems, when we talk about anchoring trees, they must be maintained. And as the tree grows and gets mature, unlike usually when we plant trees on the ground, we remove the anchoring systems, but perhaps on top of rooftops, we need to preserve the anchoring systems and even design better anchoring systems for mature trees. So we have standards, the arboricultural industry has standards for tree guying, and these are helpful to some extent, but usually they're for small or young trees, and usually the anchoring or guying is directly into the ground. When you're dealing with rooftops, you can't just punch a hole in the roof. You have to really design an anchoring system that will not harm the rooftop.
So in that spirit, over the years, we have test-driven a number of anchoring systems that are really based on like a dead man or base plate approach, so that we're avoiding putting holes in the waterproofing, because having fewer penetrations of the waterproofing means, of course, fewer potential flaws that could lead to a leak. And so here's a really early example of one thought about a buried frame that could be used to tether a root ball anchor. We can go to the next slide. Here's a later iteration. This is at Reading Hospital at their healing garden. And you can see the gray metal plates that are next to the trees. The trees are not yet placed on top of them, but those are the plates that are partly spreading out the point load of the root ball, and they're partly serving as a surface to which we can clip a root ball tether. So the tree stands on its own base plate, if you like, in this example.
And is tethered to that base plate. So the weight of the tree and the weight of the medium helps hold that tree in the ground, hold it stable without puncturing any of the rooftop.
Correct. And that works pretty well in moderate wind settings. I'm going to give you an example here from a high wind setting. This is in Hanover, Pennsylvania, at Hanover Architectural Products. This is the roof of their warehouse. It's a showpiece, a showcase landscape. And it includes trees. And at the time of installation, these trees were intended to be tethered to the base plate, just like the example you saw. So here you see the tree going in, the brown lines you see are irrigation lines. And you can see from the surrounding rural landscape, this rooftop gets exposed to a lot of wind. It's not very tall, but it's not sheltered. Get a lot of sweeping winds. Go to the next slide. So here's a photo from installation. They're taking the cables and anchoring them down to the lightweight fiberglass grate, which was a nice idea, but it didn't work very well. And if we go to the next slide, I can tell you that what happened, we had to change gears. When the tree is under enough wind pressure, that wind is moving the top of the tree. And so even though we were anchoring the root ball, the top of the tree was moving enough that the trunk was starting to break free from the root ball. It was too much top movement in these high winds for this size tree. And so the team had to scramble and provide instead tethers that came further up the trunk. And as you're probably already thinking, those ties aren't correct. They should be further up the tree and knotted differently. But you can see the scramble. You can imagine the scramble that costs in terms of having to say, whoops, need a different tethering system.
Right. And this is really different again from what we do on the ground because, we can just stake the tree, drive stakes in the ground, but you can't drive stakes into the rooftop. You have to have a new and novel system to hold that tree upright. And our current standards don't address this at all. This is why we need a new set of standards to address growing trees on rooftop structures to accommodate all the engineering needs and to accommodate the roof itself.
And to be predictive, we need to predict what conditions we think we're going to have. Go to the next slide.
Because that tree, that tree there is just 2 stories up. So even 2 stories up above the surrounding environment can really increase the wind speed on that tree.
Now the good news is that tree's doing really well. We keep track, so that tree, those river birch are doing quite well. Here's another example from Philadelphia. This is the same elevated park that we showed an early example before under the wind slides. You're looking at a chinkapin oak, Quercus muhlenbergi. Great tree actually for the wind, as it turns out. But you can see that with the white arrows, the tethering. And this was interesting because in design, we relied on the kind of dead man, another kind of dead man, like an L-shaped dead man that would sort of like a soil anchor that would resist pull out. And we realized that there wasn't enough depth in the soil. And the soil, as Jason mentioned, is quite friable. The engineered soil doesn't have a lot of cohesion. And we realized late in the game that L-shaped soil anchor was going to pull right out. So if we go to the next slide, I can show you what we did. Here you see the larger version of the opening and the lightweight insulation that makes the terrain similar to what we were looking at before. It's covered with a black filter fabric, and the crew is starting to blow the engineered media in. It's brought up from the ground, in this case with a reverse vacuum process. And the big opening you see is for the tree and the structural root zone of the tree. And here, instead of a dead man or instead of a small frame, we have actually got the ties ready for the tree that come back to a giant tie back, geogrid, which is underneath the soil. And that whole blanket of that whole layer of horizontal geogrid resists pullout the same way a tie back does on a retaining wall, or the same way your tablecloth does when you've got Thanksgiving dinner on it. So there's like a big tie back and curtain rod and tethers.
I just want to stress that these were not out of the box solutions. These were talked about and discussed and invented. They're novel solutions. But as we go and plant more trees on elevated structures, again, we need to have these as examples that work in the specifications.
And this one turned out quite well. And we didn't have to put a bunch of holes in the roof or set roof anchors to do it. So here you see on the left, the tree as it's being installed. And here you see it on the right as it is. Couple points to note. The contracting team, because this is what you do on ground, figured they could plant the tree and come back the next day to tether it. And it turned out to be windy enough, 12 stories up, that the gentleman you see holding the tree had to keep holding the tree while someone ran down to the truck to get emergency extensions for the tie so they could tie it right away. Wind was brisk enough that the tree needed to be anchored immediately upon installation. The second point to note is that the white tethers that you see going to the lawn are slack. And we did that. You're probably already aware you want the tree to move. You want to have it move enough that it stimulates the development of its own structural roots, its own adequate rooting system that is adapted to the wind on the site. And so these tethers were left deliberately slack. We slacked them progressively over the next year or two. And then after about the second or third year, we were able to take them out entirely. It was about year 3, wasn't it, Jason?
Yeah.
I think so. So in summary, the tree, this probably no surprise, but even more so on an elevated landscape, the tree must be able to move, but not too much. But you need to have above ground systems are probably where wind is high going to be more important than root ball anchoring systems that are buried below ground. But they're also stronger for those high wind solutions. And both of them need to be thought about ahead of planting. It's a lot more fuss to come back and retrofit them in after.
All right, so that was with small trees. Once these trees grow, if they're large maturing trees, you have to really plan for that ahead of time. And what we're going to talk about is really different from planting trees at grade, because these trees, they're going to spend their lifetime on the roof. So we're talking about anchoring these large trees. And this, just a forewarning, this section is somewhat speculative. We're throwing around these ideas because really they haven't been worked out. This is a new technology and we're still working on this. So it's exciting in that way that we can work with designers and engineers to help develop these larger maturing tree anchoring systems. So you have to pre-plan for these large trees, especially during high wind events. And we may have to plan for every tree, but it depends really on your situation. Is the wind going to be great enough at elevation to cause you to want to design these or install them? Maybe, maybe not. Depends on where it is on the rooftop. So, here we see that the posts are part of the roofing system, and this tree is guide to those posts so they don't penetrate it. And you can take these systems down if you want to, or put them up. So they haven't been fully fleshed out yet. Here's a system that uses the weight of the concrete structure, the pathways on top of the trees, to sort of hold the trees into place. So this is an interesting idea, that using this concrete grid structure and leaving enough room for the structural root plate and the buttress to develop adequately for these large trees beforehand, designing around that, this would hold the weight it's not the weight of the soil, it's the weight of the structure that the walkway is on that holds the tree in the ground. So it's a very interesting project in Japan. And here's a cross section of it. So these are all Zelkova trees that have been planted about 5 or 6 stories up, and they have enough soil volume, and they seem to be, even now today, they seem to be growing very well and are very biologically and structurally healthy. They haven't blown over. And so these kinds of systems are being developed around the world, but we still need help specifying them. And really, you need to work with your engineering team to do this, because everybody might have good ideas about how to adequately anchor these large mature trees to the structure in a way that doesn't hurt the structure over time. So what about the future? And these ideas are experimental. Laura and I have talked about them, and we'll discuss them soon. But roots really behave in ways we don't understand. They don't grow exactly. You can't predict where they're going to grow, and the roots grow in response to the wind loading. So we really need more long-term research on this topic of anchoring trees on elevated structures. So there's an interesting debate that we have to what the weakest link is in this for safety, anchoring trees to elevated structures. And one opportunity might mean putting some kind of stainless steel bars or something across the planting area so the tree roots can wrap around it, grow around it. And this system is anchored directly into the rooftop, and the roots grow around it. So the roots are anchored into their planting bed. So this is an idea that we have to test, and you have to talk to engineers about it, because where these wires or bars attached to the rooftop has to be designed, and all these systems have to be easy to repair, and they have to be removable, because what if that tree dies? Well, you're going to have to take the tree out. You might want to replace the soil medium and work around these anchoring systems. So you could also, as we saw in Japan, design the planters for the roots to grow under the planters and have the tree anchored that way. So the tree pit, if you will, is part of the overall concrete or overall structure of the rooftop. And there's enough room there for the tree to grow to maturity and the buttress to expand, but it holds the roots into the growing pit there. Another thing we talked about is putting panels in there so the roots can grow to these panels that are attached to the tree pit. These buttons, this is an idea I had, just putting these buttons in that are screw tops. So when the tree roots grow around it, and when wind comes trying to lift those roots out of the tree pit, they're held on by these buttons that are directly attached to the rooftop. Now, engineers, again, this is just Jason and Laura talking. We're not engineers. These things have to be designed so that the engineers can sign off on them. So there's other considerations. I'm sure you're thinking about this, on trees on rooftops. Well, okay, anchoring, tree maintenance, the soil, but there's other considerations as well that you have to be aware of, that you can at least be informed of and talk to the building team about when you're considering growing trees on rooftops.
So for example, how do we get the trees up there in the first place? Because they sure aren't going to fit in the elevator. So generally there's discussions about cranes or lifts and how to get the tree up there. How do we get the soil up there? Is it blown up through a blower truck, kind of a reversed vacuum like in the earlier picture? Is it coming up in big super sacks? all those construction logistics need to be thought through, not just for the initial installation, of course, but for any kind of maintenance or repair later. These kinds of operational logistics for horticulture and arboricultural care matter. Making sure there's water service when they're planted. Certainly, I try to remind everybody early on that not only do they have to plan for the roof being ready to receive the landscape, but to make sure that the water is operational and there's a way to care for the trees when they're put in place. The plumbing needs to be done for the hose bibs and for the irrigation system. Seasonal windows. I get a lot of questions about that. How can we push our planting window because the construction schedule didn't follow what we had in mind in the planning stage? It's not that much different than probably the questions you get for on-ground work. But also making sure you leave time to adequately test soil mixtures before installation. As Jason said, the soil, having good soil, having quality growing media is key. Please don't rely on a manufacturer's marketing information, technical sheet for the quality and the engineering properties the soil always get. Just like you would for engineered soils for stormwater infrastructure or any other topsoil, please have an independent test done and review it properly so you know that what is actually being provided is what meets your specifications. And usually it takes a couple rounds. There's always drift, and it takes a couple of rounds often.
All right.
Plan for it.
So, and I'm sure you've thought about, and I touched on, growing these large mature trees on elevated structures, what happens if they fall down? And yes, you have to design with safety in mind all the time. But trees fall in a natural environment, trees fail as well. And we have to anticipate that in our designs and in the maintenance. That's why trees on elevated rooftops, probably need to look at it and inspect them every year. And that should be built into your contract, your maintenance contract, that especially when they get large, they should be periodically inspected, but that period should be, I think, abbreviated it, every year would be good. So it's not much different than living with big trees anyway, but you have to be even more tuned to it. So there's other things like lighting. We have our lighting specifications, but we usually don't put them on every tree. But here on top of buildings, you need to have an engineer who understands your lighting system, which is in our arboricultural standards, but how to integrate that with the building's lighting system. So you always have to follow the lightning codes for roofs and buildings in your area. Touched on this, maintenance and post-planting care. Irrigation, as Laura said, you have to have that water up there before the tree is planted, or at least plan for it so when the tree is planted, you can water the tree. And you have to care for these trees during all phases of construction and then post-planting. And this is an opportunity for arborists to, have these maintenance contracts, which are specialty contracts, and you could probably charge more for these trees on elevated structures. So, that involves monitoring the moisture of the soil, because if there's problems with the tree, you have to go in and diagnose what's going on. Is it something chemical in the soil, or is it something water related, or what? Maybe you add fertilizer, maybe organic matter. Of course, insect and disease control is always important, especially if these are garden, and a lot of these rooftops are gardens. You really want these trees to look good and perform well in the landscape.
So, that's a lot to think about. It's a lot to be talking to our clients about. But, the good news is definitely trees are absolutely possible on structure. People really enjoy having them. And I think they obviously have a lot to offer for the quality of our outdoor spaces in cities. Big things, again, to recap: adequate soil volume, good quality growing media, healthy soils for long-term tree survival. No surprise, but especially important on structure because we provide all of it. And again, that's your best anchorage system. So all the great ideas, but having enough soil and having a good practice, setting the trees up for success, obviously, is the right thing to do. Certainly high wind and understanding weather patterns is going to be important, and you have to give them forethought. Anybody who has ideas about anchoring systems or is interested in more discussion about that, there's lots of room for innovation, and we'd always be up for more discussion about how to advance this aspect of the technical design.
So, again, trees on rooftops create many opportunities. They offer many benefits, and all these considerations that we discussed during this presentation, they're all solvable. It just takes, money, time, sharing of expertise, publishing successes, which is good, publishing the lessons learned, and advocating for just having green infrastructure in our elevated landscapes. These projects do excite people when you show them these pictures. They're like, wow, that looks great. And it's part of our greening our big cities in the future. I think this can become and will become, just like green roofs have become, a big component in greening our cities. So thanks a lot for joining us, and elevate your landscapes.
Trees in every country. Trees, we can work together and learn what we need to meet the challenge